Okay, good afternoon, everyone. So before the class, so first I would like to thank you guys for submitting the first paper report on time. So everyone did it. Thank you so much for that. Remember, I don't take late report submission, so please do keep up, for the next review as well. So the next paper review will be due February 2nd. So be sure to submit that on time. Okay. And also for some of you still haven't figured out the the paper for presentation, please do so as soon as possible. If you don't have access to the file, I don't know, for some reason some student cannot access to the document, send me your email address. I can share that with you. Okay. Okay. So for today's lecture, we'll keep talking about deep learning. So these will be cover some of the basics. And we'll keep talking about the convolutional neural network since we're dealing mostly image processing. Okay. Just a quick recap from last lecture, right? So here is the very basic architecture of a convolutional neural network, right? So these are the fundamental building blocks, right? The couple of operations will be in those CNN network. So one is the convolution. There's some pooling layers, and you have a flattened layer. Then you can do the classification. Okay. So the convolution is based on the intuition that some patterns are much smaller than the whole image, right? So you can do some local processing instead of connecting all the, each neuron connecting to all the pixels in the entire image. And also the same patterns can appear in different regions, right? So you can using the same filter or kernel, right, to detect those patterns in different locations in the image. And you don't have to make a different set of filters or kernels to detect this kind of repeated pattern in the image. And also the pooling is coming from, if we subsample the image, right, make it smaller, the object won't change, right? So by reducing the resolution of the image or later the feature map size, the computation can be greatly reduced. And these layers, it's just like you're building the Lego, right? You can keep stacking these different layers to make it more deep. Okay, so a quick comparison for the convolutional network and the fully connected network, right? So for this example, we have very simple grayscale image, 6 by 6. And for the fully connected layer, what you will do is in the first layer, the input layer, you have to flatten this entire image as a vector, right? Very large vector, 36 dimension. Then for each neuron in the hidden layer, you have a connection with these input pixels. But for the convolutional neural network, right? So we'll just, operating, apply these different filters on top of these original, your image, right? 6 by 6. And if you look at closely, for this particular filter, generate these feature map, right, 4 by 4. If we don't considering padding, right, and using stride 1, this is a reduced feature map 4 by 4 we generate. And for this particular, value or element in this feature map, it is connecting to only 9 pixels in the original image, right? So these are the indices of these pixels. Okay, so you can pinpoint, which pixels this particular neuron is connecting to. Okay, so for this case, for a 3 by 3 kernel, we are only connecting to the 3 pixels of the input image. Okay, so that's less parameters we have to process, right, compared to the fully connected, connecting to all the pixels. And if we using the same filter, right, we sliding across the entire image, right, we don't change the weights, right? The weights are the parameters of the filter or kernel, and we generate the other value in this feature map, right? So in this case, these will be produced by connecting to these 9 pixels. Okay, since these weights are shared, right, we are not changing the weights of the filter, and the parameters are even less, right? So as compared to the fully connected, right, if you have another one, you have another set of 36 weights, different weights connect to this neuron. Okay. So this is just a very simple example, right? 6x6 image, right? But typically in image processing or computer vision, right, you can think about what kind of typical resolution an image is, right? Maybe 256 by 256 by 3, right? 3 is the channel dimension, right? You can calculate how many pixels are there. Nowadays we have 4K resolution, right? Maybe 1,000, 4,000 by 4,000, right? So these kind of resolution, you can imagine how many pixels gonna be there if we are using fully connected layer. There's gonna be a huge number of parameters, a lot of computation. And that's just for image, right? If you think about if you're dealing with 4K videos, right, you have to apply this frame by frame. So the computation is gonna intolerable for some of the modern computing platforms. Okay. So here I have 2 questions. So one is, what kernel size to use, right? In previous example, we use these 3x3 kernel size, right? Of course, you can specify other size, for example, 5x5, maybe 7x7, and you can even larger, like 12x12. And the other question is how many kernels to use in each layer, right? So, you are building a deep neural networks, right? Each layer you have to, convolutional layer, you have to specify how many kernels or how many filters you want to use. So how do we come up with these different choices? Yeah, so Nikhil, you were saying a larger or smaller amount of pixels from the filter of a large or small image. So you were saying, okay, if it's a large image, you want to using a large filter, right? So that's your kind of rule of thumb to select the kernel size. Okay, yeah, that is reasonable, right? So if you have a large image, right, maybe you use a very small filter, you don't get much information in that small window, right? I was trying to come up with a very good analogy. Is you can think about you are using a flashlight, okay, and you're using this flashlight kind of illuminate like on a wall, right? Then you can see the region of that flashlight covers, right, the light. Okay, so that could be your kernel size, right? If you move move far away from the wall, right, then the light will cover more region, right? If you move close, the region of your flashlight cover will be smaller, right? So you can think about that's the kernel size, and you are scanning through this entire image, right? So it'd be like a flashlight across different rows and columns. Okay, so yeah, definitely, maybe for a larger image, maybe a larger kernel size will give you some benefit of capture more contextual information, right? Also, this will extract some useful information so that the later layer can keep building upon. But in general, there's not like a definite or like the golden standard for what kind of kernel size to use. It mostly will be some kind of engineering choice, okay, and based on some empirical analysis, right? You can try different kernel size. Maybe you can try 3x3, 5x5, 7x7, and see which one is the best choice for your particular application, okay? And also, you can think about like this 5x5 kernel is essentially 3x3 kernels like back to back, right? You can lay 2 convolutional layers. Of course, you have a pooling there, right? 3 by 3, then pooling, then 3 by 3 is, the effective, receptive cell size for these two layers of 3 by 3 is essentially 5 by 5, right? So you can, maybe some of the situation, they are kind of close, the effect eventually, okay? And also the number of kernels to use is also, there's not a golden standards. So if you look at some of the classic deep neural networks like AlexNet, VGG, ResNet, DenseNet later. So different layers, they specify different number of filters, okay? So those are also based on the, kind of empirical study or experience. And of course, one thing to remember is that if you increase the channel size or the number of kernels, right, the computation is also increased. So that's something you have to, keep that in mind. If you want to build a network for your application, do you also care about the computation efficiency, right? So in this case, you have to come up with a better, trade-off between the accuracy and efficiency, right? Or, maybe if you have more, layers, more kernels or channels, it will help in terms of accuracy, but your computation complexity can also be increased a lot. So that's something you can keep in mind when you design your own network architecture, okay? So here are some of the other, there's a couple of other variants of convolutional operation. So one is the so-called dilated convolution, which I'll talk in the next slide, and also depth-wise separable convolution. So this one and the last one, grouped convolution, these two are designed for computation efficiency, especially this is introduced in MobileNet, right? So people want to deploy deep neural network on some mobile platform like your cell phone or maybe some IoT devices, right? Obviously, the computation resource or memory resource are very limited, right? You cannot deploy a very deep, large network. So you want to come up with some very, computation and memory efficient architecture. So these are the two variants that is specifically designed for reduce the number of parameters, and also the number of compute, the floating point operations. Yeah, so if you are also maybe in your course project, you are aiming to develop some of the efficient neural network architecture, these two are very good choices you can use, especially this stepwise separable convolution, very popular, very common. Okay, so here is like an animation for this dilated convolution. Okay, so on the left, you can see this is the the normal convolution, right? So I have a 3 by 3 kernel, right? So I kind of scan across this image, right? Do this kind of dot product on this 3 by 3 region. Okay, but for the dilated convolution on the right side, okay, in this case, we have a dilation rate equals to 2. So basically, you are not sampling the pixel like a consecutive pixels in these regions, right? So you kind of every 2 pixels, right? You select one, right? So this is obviously governed by the dilation rate, right? If you have a large dilation rate, then you will cover a more region, right? The interval you are selecting the pixels will be larger, okay? So if you look at these the pixel, right? This dark blue here, okay, although it's constantly moving, but you can see, right? So these dark blue, you're still selecting these 9 pixels, right? In total of 9 pixels because your convolution kernel is 3 by 3. It's just the dilation rate is different. So for this case, you have dilation rate equals to 1 on the normal convolution. Here is 2. As you can see that, the actual region you are covering is actually 5 by 5, right? Although there's some, pixels in between we didn't select, but in this region, we are able to at least sample some pixels from these large 5 by 5 region, okay? So the benefit of this dilated convolution is that you don't increase the number of, parameters or weights, right? If you want to cover a 5x5 region, then the normal choice is you can using this 5x5 convolutional kernel, right? The normal 5x5 convolutional kernel, I mean. But if you're using a 3x3 with a dilation rate equals to 2, you are able to cover these 5x5 region, but the total normal parameter doesn't change, right? It's still going to be the same as 9x9, right? You have less parameters as compared to using the normal 5x5. So that's the advantage of using this kind of dilated convolution. And it is typically used in segmentation task, right? If you're doing image segmentation, that is, you want to assign a label for each pixel, right? The context information obviously is very important, right? You want to, maybe this is an edge, right? You want to look at a large, region, know the context, right? What's the neighboring object that is? So you're able to, correctly predict this pixel maybe on the boundary of this particular object, right? Okay, so yeah, so this normal convolution, right? So you have a dilation rate equals to 1. Here you have a larger dilation rate, right? So you can cover more larger local regions, and you can even increase the dilation rate even further, so that your field of view is going to be much larger. Okay. And so for some of the technique, you can using multiple dilation rate. Okay, say you can using the normal convolution 3x3 with dilation rate equals to 1, and you can also using another set of filters or kernels with dilation rate equals to 2 or 3, and another set of kernels to set dilation rate even larger, like 6 or even 8. So in this case, you are able to capture this kind of multi-scale, multi-resolutional feature, right? So you have this finest, and here you have more towards more global information, right? When the dilation rate increases. And here's some of the segmentation outcome, right? So this is if you're using just the normal convolution, you're just using a slightly larger kernel size, this is the segmentation outcome. But here, if we're using different dilation rates, right, capture this kind of multi-scale information, the segmentation results are better, right? Because if you look at this model cycle here, right? This is pretty narrow region, right? So you can easily mistaken this maybe to some background object, like mixed with the background trees or etc. But if you're using this kind of multi-scale, using different dilated rate, you are able to model multi-scale information to generate better segmentation result. Okay, so that's a couple of variants for the convolution. And later, I think when I talk about some of the efficient network design in medical image segmentation, I will touch upon the depth separate convolution. But for now, we'll just if you understand the standard convolution, I'll be fine. So next component is the max pooling. So the max pooling is, the objective is to reduce the feature map size, right? And let's say this is one filter you are using, and this is the feature map has been generated. And for another filter, you will generate another feature map, okay? And what max pooling does is you can, specify the region, right? So typically we're using 2x2 max pooling, okay? By the name max, that means you'll take the maximum value in this region, okay? So you just look at these 2x2 region and you take the maximum, okay? Of course, you can increase your pooling region, right? Here, just 2x2 is very normal. You reduce the feature map by half. You can increase like 4x4, right? That will reduce the image size even further. But you don't want to do this pooling aggressively, right? You want to, like for one layer, you from original size reduced by 1/8, right? Then you end up with a lot of information is lost because of this large pooling layer, right? So you want to do this gradually, maybe half, then you do this, and again pooling by half, right? You gradually reduce the resolution rather than just go directly to the minimum, like, or the desired resolution you want. So that's going to be resulting in a lot of information loss. Okay. So you can see how this max pooling works, right? Just take the maximum of this pooling window. And this applies to all the feature maps. Okay, so this is one, then you do the same for the next feature map. Okay, so now you will just leave these pooled value, right? The maximum value for each pooling window. Okay, so in this case, you're resulting like a reduced feature map size, right? Originally you have 4x4, right? So now you have 2x2. Okay, so basically, if you go to the convolution after the max pooling, you basically end up with a new image or feature map, but with a smaller size. Okay. Okay, so this is, again, just reiterate, after the max pooling, you have a smaller size than original image, and the number of channels is going to be corresponding to the number of filters you're using for each layer. And as we mentioned, right, so pooling is able to reduce the spatial size so that you can reduce the number of parameters and the computation in the network. So that's the main purpose of doing the pooling. And there's actually another way to do the pooling. If you reduce the size, if you don't want to using the pooling layer, you can also using the large stride of your convolution, right? Even though for before we are using stride equal to 1, if we don't use padding, right, we are still reduce the size. Every time we can reduce by 2 dimension, right? But if you use a large stride like 2 or even 3 or 4, right, so you are also able to reduce the feature map size, right? Because when we do the convolution, we skip a couple of rows or columns, right, to next to the next window for doing this kind of element-wise multiplication. So that's another way to reduce the feature map size. That is using the large stride for your convolution if you don't want to using the pooling. Okay. So so max pooling obviously come from the maximum operation, right? You take the maximum in that pooling window. There's other options, like you can take the average, right? So that will be average pooling. So in this case, for this window, right, instead of take the maximum, I'll just take the average, right? For this case, because all the values are the same, so the average can be -1. But for this case, right, the maximum is -1. Maybe this example better. So the maximum is 3. Okay, this one will be kept. So if we take the average, right, so you end up with the value of 2, right, in this window, not the is not any original value from this feature map, just the average. Okay, so for the pooling layer, so is there any other benefit we are doing this, right? Except, we can reduce the spatial resolution and reduce the computation. Is there any other benefit? So I will kind of touch upon on that, right? So when we reduced the feature map size, right? If you're still using, let's say, using a 3x3 kernels all the way, right? All the layers, convolution little layers, you decide to using 3x3 kernels, okay? So when you reduce the feature map size by half, right? If you still apply the same kernel size, So in that layer, your receptive field will be larger, right? Let's still consider that flashlight example, right? If you're standing there, the same position towards the wall, right? So which means your flashlight, the light region is fixed, right? If your image reduced by half, you can imagine your flashlight region will cover a larger local region, right? You capture more information. So this is another benefit of doing the pooling, right? By reducing the resolution gradually, you also gradually capturing more or larger, field of view. So you are able to extract more contextual or global information to build a more informative feature representation. Okay. Okay, so we are already talk about the convolution, max pooling. So towards the end, we will do the flattening layer. So basically, you just collapse all the feature maps. Let's say for this example, we make it simple, right? Let's say you only have 2 feature maps, and each has a resolution 2 by 2, right? When you collapse these feature maps into one large vector, right? So you end up with, these flattened layer, one vector has 1 by 8 dimension. Okay, so basically just form, vectorize these feature maps into, giant vector. And then you can, connect with these fully connected, a couple of fully connected layer. Okay. So here are some of the code, for implementing a CN in Keras. So Keras is a deep learning API that is built upon on the TensorFlow platform. So the basic, some of the usage will be very close to PyTorch. Okay, I'm just here using Keras as an example. Okay, but some of the operations, although the function name is going to be different, a little bit different than in PyTorch, but the idea how to construct or build your network, the layers, the structure are going to be very similar. Okay. So first we'll do the convolutional 2D convolution, right? So you're using this convolution 2D, and you can specify the kernel size, right? 3 by 3, and how many kernels or filters you want to use. Okay, if here we want to use in 25 kernels or filters, and this is the 3 by 3 size. Okay, and we also specify the input shape. Okay, the input is a 28 by 28 by 1. Okay, 1 is the channel dimension, so which means we have a 28 by 28 grayscale, right? 1 channel image. Okay, so if this number here equals to 3, then that's the RGB, right? We have 3 channels. And this is just the resolution of your image. Okay. And so as mentioned, we have 25 3 by 3 filters. So that's specified for your convolution layer. Okay. And for the max pooling, right? So we do the max pooling 2D, right? You specify your window size 2 by 2, which is very common. And so you're basically, selecting the maximum from that window. Okay. So let's say we have an input, right? For this example, we know input resolution 28 by 28, and we using 25 3 by 3 kernels in the first convolutional layer. So the resulting feature map will be 25 corresponding to the channel size, right? Because we're using 25 filters, right? So that's one filter generate a one feature map. That is one channel. Right. If we don't do padding and we use stride 1, we generate feature map size 26 by 26. That's the spatial size. Okay. And we go through a max pooling layer, right? 2 by 2 pooling, we reduce the spatial resolution by half, right? So we have 25 channels, doesn't change, right? Because pooling just reducing the spatial resolution. That is 13 by 13. Okay. We can apply another convolutional layer. So in this case, we fix the kernel size 3 by 3, But in this layer, we decide to double the kernel numbers, right, or filter numbers. We're using 50 instead of the first layer. We're using 25. We decide to using more kernels or filters, 50 filters. So in this case, we are generating the feature map size has 50 by 11 by 11. Okay, so 11 by 11 is the spatial size, and 50 is the channel dimension. Okay, and you can do another pooling layer, then you're generating, reducing the size by half. Okay. So here, let's see, let's kind of stop at this first convolutional layer here. So I have one question that is, how many parameters are there for each filter? Anyone? So this is the first convolution, right? So how many parameters are there for each filter? Yeah, 9, right? That is because we have the spatial resolution 3 by 3. And because of the input, right, it's just one channel because of the grayscale, right? Your channel dimension or your filter will be the same as your input, right? So you can think of that's 1 by 3 by 3, right? So that's 9 parameter. Okay. And how about this layer, the second convolutional layer? How many parameters for each filter? It's gonna be 225, right? Why is that? You have 3 times 3, and you also have the channel dimension of 25, right? Because the input now, right, after this max pooling, that's the feature map the network have right now, right? 25 by 13 by 13, that's the channel dimension, right? If you want to apply another conv layer, right? So you want to match the channel dimension 25, so you have 25 by 3 by 3, that's your filter size, okay? So that's gonna be 25 times 9, 225 parameters for your filter, okay? So we can go on to, to this last max pooling. So you end up with 50 by 5 by 5, right? Now, what we want is we want to connect to a couple of fully connected layer, okay? Because, the reason we want to build a couple of, fully connected layer is that, eventually we want to, every pixels had the chance to exchange or has had the chance to connect to the neuron, right? Trying to exchange the information, because all previously we are just looking at local information because of this local convolutional operation, right? At the high level, because we are reduced the size, right? Eventually we want to using fully connected layer to exchange, more information. So in this case, we'll add like a flattened layer. Okay, so that in Keras here. So basically collapse these feature maps into this size. Okay, 1,250. Okay, then you can maybe attach like 1 or 2 fully connect layer. Okay, then you can generate the output, the probability. Okay. So here I'm adding, one fully connected layer that specify 100 dimension. That is, in this fully connected layer, I have 100 neurons. Okay, and also using activation, using ReLU activation. Then the output will be another dense layer. Here, probably I'm doing digit classification, right? So I specify 10 classes. And then I using the softmax layer to trying to map whatever the output you have here, trying to map between 2D range between 0 and 1, right? We have a better interpretation in terms of probability. Okay, so that's how basically you can construct your neural network. Okay. Okay, so speak softmax, right? Last lecture, we also talked about that, right? So it's basically you want to do some normalization because you want your output has a very nice, interpretation, right? Because arbitrary number is difficult to interpret. What that does that mean, right? But if we're able to normalize that and make it in the range of 0 to 1 and sum them together equals to 1, that we have very nice probability interpretation. Right. So if you have a large probability, then there's a high chance, right? This particular input belong to that class. Okay. Okay, so now we kind of know all these different building blocks, right? And those count layer, max pooling, flatten, then doing a couple of fully connect layer, and doing the softmax to map to some of the probability output, right? And eventually, we have to kind of using the training sample, right, to optimize, those model parameters, right? Remember in the last lecture, we mentioned the neural network is basically a mapping function, right? There's a set of functions, right, you can choose, right? But what is the best mapping function, right? And these functions are basically determined by these network parameters, theta, right? If you change the parameter, then the function is going to be totally different, right? So we want to try to optimize these network parameters. So we want to specify a goal, right? How to define or measure how good is the network performing, right? So if we have a labeled data set, right, doing the supervised learning, that's using the classification as an example. Okay, so we're doing image classification, and the direct measurement is the prediction or classification accuracy, right? So for the network training optimization, we can come up with a loss function, right? Because we have the ground truth label, we can measure how good is your prediction. Okay, and for each sample, we can measure a loss or a cost, right? If it's not like a perfect prediction, there's going to be some cost, right? Because you are making some errors. Okay, there's a cost involved. So next time, try harder to come up with better parameters so you can make, less error. Okay, so your cost can be reduced. Okay, so that's the idea for the optimization. Okay, so in terms of formulation, right? So you have a loss function L, right? L stands for loss, or you can using, as this cost. That's basically the same. And W is network parameters, right? So we consider all the parameters of your network, right? Different layers, all the parameters, we lump them into this giant matrix. Okay, so that's your network parameters. And you have, obviously you have input, right? For, training data set, right? You have maybe thousands or maybe, 10,000s of, samples here. So you have an Xi, you have N training samples, okay? Each training sample, you have a ground truth label, Yi, okay? So this is like an image and a label, so. And for each of the training sample, right, you can compute the loss, right? Eventually, we want to sum them up, right? A total of N training samples, what is your total loss or cost? Okay, so that's your, loss for the entire training set. And here, I'm just using this digit classification, right? So this is the handwriting digit, right? So you generate a prediction, right? We are using Y hat to indicating this is the network prediction, and this Y is the ground truth, right? Or your target, and we using the one hot encoding, right? So the correct class will be labeled 1, the other class will be all 0. Okay, so this one indicating which class it belongs to. And so if we have the prediction or also have the ground truth, right, we can measure the loss, right? There's a lot of ways you can measure the loss, right? So the one common one, and maybe you can think of, is the squared error, right? You just compute the Euclidean distance. You can measure how close your prediction as compared to this ground truth. Okay, so that's one loss you can use, squared error. And another, which is, most of the time people using, is the cross entropy loss. Okay, if you know logistic regression, okay, so this is the binary cross entropy loss. Okay, so basically, this is the equation for the loss, right? So y is the ground truth, y hat is the prediction. Then let's see why this makes sense. Okay, mean square error is easy to understand, right? You compute the difference. But what does this mean here, right? So it seems to be very complicated, right? What does this mean? So let's look at how, maybe work on a specific example here. Let's see. Okay, so I'm plot this log curve here, no matter what kind of, either natural log or maybe 10, right? So these are the curve right here, okay? Let's say my ground truth y is 0, okay? Let's consider this binary class 0 or 1, okay? Let's say in this sample, my ground truth is 0, okay? So this term disappear, right? Because multiply with 0, and 1 minus 0, that's 1. So you have log 1 minus y hat, okay? Y hat is your prediction, okay? So let's say my prediction, so remember this is probability, right? So my prediction is 0. Let's say my prediction is 0.9. Okay, for logistic regression, if it's above, the threshold of 0.5, that will go to the class of 1, right? Because your prediction 0.9, that is close to 1. Okay, so in this case, because the ground truth I mentioned, it is 0, right? But your prediction 0.9, which indicating you're predicting the class of 1, which is wrong, right? So let's go to this curve and look at here. So you have log 1 minus 0.9. So that's log 0.1. Okay, so where that is located, right? So I'm not sure if you can see this clearly. So this region is 0, between 0 and 1, right? So we are computing log 0.1, okay, which is very close to 0, okay? If you look at, let's just look at, pick a natural log, okay, this green curve right here, right? You have a very large number, right? Log 0.1. You can use in calculator if you want to generate the exact number, but it's some number pretty large, right? Maybe maybe -3 or something, right? Because there's a minus sign there, right? So you have a +3. So that's a large loss for you. And that's intuitively makes sense, right? Because you make a mistake, right? You are predicting 0.9, right? Very close to the class of 1. Okay, so you are making a large mistake, okay? If you're predicting 0.6, right? But still you will classify as a, class 1, which is wrong label, but you are moving towards in the middle, right? So you are incur a less loss because, as compared to you are making a mistake of 0.9, 0.6 a little better, okay? But if you predicting 0.2, okay, right, which is very close to 0, right? Means you are making a very correct prediction. So we are computing, log 1 minus 0.2, that is log 0.8, right? Which is very close to the other end, which is 1 here. Okay, if you look at here, we are incur a small loss, right? If you predict exactly 0, which you make a perfect prediction, right? We are computing log 1 here, which is 0, right? You are incur a 0 loss, right? That's makes sense, right? You're making a correct prediction. I don't want to penalize you, right? Penalize the model because you're, making a very good prediction. So there's no loss incur. Okay, so that's, you can see how logic these cross entropy loss in terms of classification. Okay, so for the general case, right, if we have multi-class classification, we consider K classes. This is the general form, okay, for the cross entropy loss. So basically, you sum the the probability of the ground truth for that for the sample, right, and multiply with your prediction, log of your prediction probability, right, over all the classes. Okay. And here is an example here, right? So remember, because we are using the softmax, right? So your prediction will be, the numbers, just a probability, right, between 0 and 1. Okay. So this is like a very simple example, right? I have 3 samples here, right? This is the model predicted output y hat, right? This is y1, y2, y3, right? Each of these 3-dimensional output vector probability. And you compare with these targets, right? Which is 1-hot encoding. Okay, so you can compute these probabilities, right, for each of the loss, and you can sum them together, right? If these 3 samples here, you just basically sum them together. That's your total loss for the training. Okay. Okay, so here, back to the digit classification, right? Before we using the squared arrow, now we using the cross entropy, and that's the loss we'll use to compute for your training set. Okay, so for the classification problem, typically we're using cross entropy. So for this mean square arrow is mostly used for regression problem. Okay. And in Keras, so it's very easy to specify, okay, what kind of loss you want to use. Okay, so for, if you're doing some regression, right, you want to using the mean square arrow, so you just specify MSE. If for the classification for fun, you want to compare with cross entropy, you can also using as an MSE. You can specify that, right? And yeah, obviously this will be like optimizer we'll talk about later. This is the learning rate, right? The matrices measure is for is using accuracy. So for the cross entropy, you can using this categorical cross entropy to specify that I want to using cross entropy as the loss. Okay. Okay, so now we have the network ready, right? We have specified all the architecture of the network, and we also have the training data set. We specify the loss function, right? Maybe using cross entropy as the loss. And what left to do is train the network, right? Optimize the network parameters so that you can reduce your total loss, for the training set, right? And for typically for the training process is that we'll have these, sampled, labeled data, right? We feed them into the network, right? Get the prediction, right? And we can compute the loss or errors, right? Compare that to your prediction to the ground truth, right? We can using gradient descent, back propagate the error, and it will use that to update your network parameters or weights, right? So the network parameters are kind of tuning knobs, okay? These are the supervision signal, okay? How you want to tune those knobs, so in the next forward pass, maybe you can make less mistake, right? Less error, okay? So we do this iteratively, okay? So, gradually reduce the loss. Hopefully at the end, maybe your training converged, you are able to have a very good model that is able to make a very good prediction accuracy, means less, training error, okay? So for the gradient descent, that's like the mostly commonly used for optimization, right? So we, for updating the network parameters, right? So each iteration, right, we have the theta new, indicating this is the updated parameter, right? Old is maybe your previous iteration, and we compute these local gradient, okay, in terms of the loss, okay, J here. And we also have a learning rate alpha, okay? And we compute the gradient and we do the update for all the parameters, okay? And because of the network has multiple layers, right? So for each of the layers of the parameters, we have to do this kind of update using gradient descent, okay? So we are using the chain rule to compute what is the local gradient, right? Because we have many layers, right? What is the gradient, for one particular neuron, right? At one particular layer. So we have to compute that local gradient. So we can using the chain rule to get those local gradient for each of the neurons there. So you don't have to compute these by yourself. Okay, so if you're doing some of the network training, so all these modern deep learning platform has already figured it out, right? These backpropagation compute these local gradient. You don't have to worry about these, so they will automatically compute that and do the backpropagation. So you just have to specify what kind of optimizer you want to use. Okay. But yeah, the gradient descent, basically this is the fundamental for the gradient descent, right? Just to update the parameter. And one important parameter is the learning rate, right? That controls how your model parameter update. You can have, typically this is value between 0 and 1. You have to specify one particular value for your learning rate. Okay. Here I have one question for you guys. So why in the gradient descent there is a minus here? Like my old parameter minus these gradient we multiply with this learning rate, not plus. Anyone knows? Okay, so maybe we can look at this quick example here. Okay, so let's just draw axis here. So let's say my vertical is the my loss, my cost function, right, J theta. And this is my model parameter, okay. Let's say, okay, this may be my, loss curve, maybe look like this, okay. Remember, the goal is we want to minimize the loss, right? Minimize this J theta, right? Minimize this cost, okay. Let's say I have, maybe I have two points here. Let's just look at this one. Okay, and what is the gradient? Basically, that's the slope, right? You compute the slope, right? Okay, so that's your gradient here. Okay, alpha is a positive value, right? So here the slope is what? Is positive, right? We don't know exact value, but we know that's positive, okay? But for this one, we compute the gradient, the slope, okay? What do we know for a fact is negative, okay? So if at this particular time, right, your parameters is located here. Okay, I want to see what's the next, where should I move, right? How should this theta move along this cost, right? Is it moving left, right? Like how do we optimize towards the minimizing the cost, right? Since we know we want to minimize the cost, right? For if I'm right here, minimize the cost means I want to go downhill, right? Maybe towards this local minima right here, right? So I want to go towards the left, right? So if I'm here, right, I'm minus some positive value, right? I know the slope is positive, right? So that's here. Alpha is positive, right? I'm minus some positive value, right? Which means I'm moving towards this direction. Maybe I move next step, I'm moving here, right? That's the right direction to go, right? Because I'm trying towards these, minimize the cost toward these local minima, okay? But for this one is right here, right? The slope is negative, right? So then we basically want to plus, is your negative here, you have negative value, right? Basically this theta O, the plus some, positive value, right? Which means we moving towards this direction. Okay, maybe next step I'm moving towards here, right? And this also makes sense, right? Because I'm aiming towards these local minima, right? Trying to minimize the cost. Okay, so basically all this gradient descent, that is you want to try to minimize your cost, maybe reach to local minima. Okay. Yeah, so no, the loss function is your cost, right? That's your loss, right? How much error you're making. You want to minimize that cost, right? Remember, you are generating a prediction, right? You are measured that, your prediction with the ground truth, right? So that's your if you're doing a perfect prediction, right? Your error, your cost should be the loss, right? The loss should be zero, right? Because you are not making any mistake, right? You want to minimize that loss function, right? So if you're using cross entropy, using mean square error, right? So that's the cost you will have. You want to minimize that. Okay, what are the consequences of using a large versus small learning rate in this scenario? Okay, so that's a good question. So we will later talk about that. Okay, so also when we compute this gradient, right? So one thing we also mentioned in the last lecture is these activation function, right? So for one commonly used activation function is the ReLU, right? So this is the ReLU, basically the maximum between 0 and z, right? And because of the ReLU, right, you have the left side playing with 0. If you compute the gradient, it's going to be 0, right? So that's going to be problematic. If you multiply with 0, and everything won't change anymore. Okay, so to address this issue, there's some variants like leaky ReLU, parametric ReLU, right? So you're using some of the certain slope on the left plane. So you are not end up with just a 0 gradient. You still have something there. So for this parametric ReLU, you actually can specify like how what the slope is going to be on your left side, right? Alpha is also like a parameter in this case. You can learn, like choose what's the best based on the gradient descent optimization. Okay. And for the gradient descent, typically we won't, compute the true gradient over the entire training data set because usually those training data set will be very large, right? Computing that is not very practical because of the computation and memory limitations. So we want to take maybe a shortcut, right? So we can using a mini batch, so-called mini batch of the example, right? Instead of using the entire data set, each compute the total loss, compute the gradient, we'll just take a mini batch of the example. Okay, mini batch means maybe I take, let's say I have 10 millions of training data. Okay, maybe a mini batch can be 1,000. Okay, that gradient, we use that as an approximation of the gradient as if you were computing from the entire data set. Okay. And this is how, we take this kind of mini batch training paradigm works. Okay, so still using the digit classification as an example. Okay, so in the beginning, we randomly initialize the network parameters, right? That's what, that's basically what we can do in the initial step. We just randomly initialize. And then we pick the first batch, okay? Maybe your training has a lot of examples, let's say 1,000 examples. Okay, for this batch, I'm going to specify my batch size, right? Which means how many samples I'm going to pick. Okay, let's say we consider 50 samples for your batch size, right? Every time I'll randomly select 50 samples, from the entire training set. Okay, so first batch you pick 50 of them, and in the second batch, okay, I will pick 50 samples from the rest of those remaining samples. Okay, so the goal is I want to eventually pick all the samples from the entire training set, right? So whatever the first batch I already picked, I'm not considering that anymore. Okay, I'm going to pick 50 from the rest of the samples. Okay, so we can do this, until all the samples has been exhausted in the entire data set. Okay, so for this process, we call this one epoch. Okay, basically this is called one iteration. Okay, just one batch. But if we do this multiple times, exhaust all the examples in the training list, we call this one epoch. Okay, basically you've examined or kind of forward all your examples in the training set to the network. We are able to perform some of the model update from one epoch. Okay, and once you complete this one epoch, okay, you can repeat the same process, right? You start from the beginning and do this again. Okay, typically for the model training, you will maybe do let's say for ImageNet classification, ImageNet is pretty large data set. You can do maybe 100 epochs, or some people training longer epoch, like 200, 300 epoch even. So and obviously if you train longer, right, if you specify larger epochs, you will you have more longer time to wait for the model to finish the training, right? So that means you have longer time for your training process. Okay, so for the code here is also very simple. You can specify the batch size, right? Batch size depends on your hardware limitation, right? Typically is limited by your GPU memory. Okay, if you have a large image resolution, right, that each image will occupy a lot of memory, right? So you may not able to specify a large memory batch size, because your GPU memory cannot fit that many images, right? If your model size is also very large, that will also affect your batch size. But the rule of thumb is that large batch size will perform better than the small batch size, because from this kind of statistical point of view, right, you have more data, right? You have statistically more meaningful to approximate your global gradient. Okay, so you can try to specify a batch size that maximally fits your GPU memory. So that's the rule of thumb when you do this kind of deep learning training. Okay, and also you can specify how many training epochs you want your model to train. Okay, so for the optimization method, right, we talk about gradient chem. So gradient descent. There's also other optimizers. So the other very popular one is the Adam optimizer. So you can just specify Adam in your PyTorch or Keras, right? Specify that particular optimizer. Okay, so if you're interested, you can track their papers and see what's the difference between different optimizers. Okay, so here's the question you've asked, right? How to pick the learning rate, right? Should I pick a smaller one or should I pick a larger one, right? So the answer is, there's no learning rate can rule them all, right? So there's no like this one particular learning rate is the, definitely you can choose to apply to all the applications. It depends, okay? But the general rule of thumb is that you can start from a high value and you can keep cutting them by half if model diverges. And I think I have a figure here, okay, which is not, okay, that's fine. So let's look at what if you pick too large of the your learning rate, okay, let's say this is your cost function here, right? So if you pick too large of the learning rate, okay, you make a very large step, you know, because you do, the alpha is very large, you do a large step, right? You maybe jump here, okay? You are right here in the next step, okay? Then in the next step, maybe if the alpha is large, I'm jumping here, okay? And next step, I'm jumping right here. Okay, I'm jumping out, right? You can see maybe you will have this kind of divergence effect, right? You jumping, you know, irregularly here, you know, towards this kind of landscape. Okay, so that's the behavior called diverge, right? You are not converged to a local minima, right? You have these large step makes you jumping back and forth. Okay, so that's one risk we don't want to. That's called diverge, right? But obviously, smaller learning step, right? You're taking baby step, right? It's not bad, right? As these diverge case, but you are making too small progress, right? Each time you make a very baby step, right? So the downside is that, okay, you take too much time to converge here, right? Because every time just make a very small, tiny step, right? And then you end up have to make many steps. You are able to achieve this goal, okay? So a just right in a learning step will quickly take you there, maybe a couple of steps, but won't able to shoot out of these local minima, right? Like the diverge case, okay? So, and the reason we starting with the large is that maybe in the beginning, you can quickly, right, reach this region, okay? When you coming down towards this local minima, okay, I want to take a baby step, right? To preventing me from jumping out here, become this diverge case, right? So you can take quick step, then eventually, you know, make a small step towards these, you know, local minima. So that's the idea, okay? And you can also using this kind of learning schedule, right? Maybe after 10 training epoch, I want to reduce my learning rate. After another 10 training epoch, I also want to reduce my learning rate further by, you know, 10%, right? So that's the strategy you can use, okay? Yeah, so if you have this kind of, you know, basically if you have a smaller learning rate, right? So you multiply with gradient, right? So the very small learning rate, right? Zero, I'm talking about 10 to the negative 5 or 6, these kind of numbers, right? So you are making very tiny steps here, right? But if you have a larger learning rate, then you have the risk of this kind of diverge phenomena, okay? So these are the rule of thumb, right? You can using learning rate schedule, right? You can using a large learning rate in the beginning, not very large, a decent learning rate. Then you can gradually, you know, reduce them, right? Just like you're taking precaution, right? In the beginning, you can be a little bit bold. That's fine. Maybe you still have room to go, right? Maybe towards in the middle, right? Maybe a quarter. I want to gradually, you know, take a small step. So I'm able to eventually reach that local minimum, okay? Okay, so that's what you will see from the loss is that, right, a good learning rate, which is the red line here, right? So you are able to see this nice curve, right? Gradually reduce your loss and eventually plateaus, right? When you reach this local minima, okay, no matter how you move little by little, you are not able to, you won't get much of the benefit, right? So because you're already at this local minima, okay? So you will see this kind of plateau region. So very high learning rate, right? So you reduce, then suddenly jump up, right? So maybe you jump here, okay? Jump here, take a large step, you jump to here. Okay, then you will incur a very large loss. Okay, so then you can see this loss kind of jump to the sky, right? And here the low learning rate, right? So you know, eventually there's still room to go, right? Let's say this is 100 epoch, okay? If you have a smaller learning rate at 100 training epoch, although it's behaved nicely, right, reducing, not like going up, but there's still room for you to go, right? Maybe another 200. If you look at this progression, trend, right? You draw it like this. Maybe you need another 50 of 100 epochs to reach this level, right? So then this ways, they're gonna be consuming you more time and more compute, right? So, this is also not a very ideal case, right? We want to have a very nice, learning loss curve that is able to reach this local minima quickly, and also, guarantee you able to reach some of the local minima. Okay. And we also, when we train the deep neural network, we often using some regularization technique. So the reason we want to using regularization is that this is not just for deep learning. Any classical machine learning model, like logistic regression, support vector machine, or some other machine learning models, you also have the risk of overfitting. Okay, overfitting means during the training, your model is trying too hard to make perfect prediction for the model. Remember last lecture, I give you like an example, right? You have two classes, right? They are not perfectly separable, right? So maybe I have another class like here. Right, so overfitting means my model trying very hard to come up with a decision boundary, right? We go around a very complex decision boundary, trying to perfectly separate these two classes of data in my training set, okay? And to reach maybe 100% accuracy, okay? But the model is not able to generalize well, right? Because if my test data set, okay, if my test data set is like this, okay, why do you need such a complicated model, right, to make this kind of wriggle, right? I make mistake here, right? So that means this is overfitting, right? You're trying too hard for your training data set, okay? Your model is way too complicated, is not able to generalize well because all they remember is the training data, right? How they behave, trying to classify them correctly. But for some testing data, unseen data, they change some changes in not able to classify them well, okay? So this is usually caused by some of the large weights, right? So for your model, so we can using some of the regularization term like L2 norm to penalize those large weights, okay? So we're using this term, right? The square of your weights, right? We can penalize your the large weights, right? Because if you have large weights, this will be very high, right? The overall. Okay, so we also have other technique called the dropout and also early stopping. Okay. So I think we don't have time right now. So maybe we can leave the rest for the next lecture. So I do want to spend a decent time on this. So because a lot of techniques are very important. When you do this kind of project and also your programming assignment, these are some of very useful techniques to stabilize your training. So it's worth to spend some time to understand how they work and how you can use them in the practical, training your network. Okay. So before we end here, any questions? Okay, so if you don't have any questions, I'm gonna end here and we can pick up the rest from the next lecture, okay? All right, thank you guys. Have a nice weekend.